canvas to find the property. Hi everyone, question 1 tutorial 2. In this question we have 1, 2, 3, 4, 5, 6, 7, 8, 9 small questions. Okay, and we will start with the question 1. Find vapor pressure water at 5, 20, 50 and 100 Celsius. With this question we can use the table on the canvas. We upload on UTS online for you already. Okay, and the table you can find here is in the appendix, property tables and charts. And properties of water is, you see the properties of saturated water is table 8.3. Okay, table 8.3. You have to find the vapor pressure of water at 5, 20, 50 and 100 Celsius. And vapor pressure is the second column on this table, saturation pressure, PSAT. Okay. For example, at the temperature is 5 Celsius, the set PV vapor pressure is 0.8721 kPa. Okay. At 20 Celsius, we have vapor pressure is 2.339. At 50, we have 12.35. And at 100 is 101.3 kPa. This one is atmospheric pressure at sea level in the standard condition. Okay, so for the first question, you can use table 8.3 to find vapor pressure. Okay, so the first one, you can use the table 8.3 to find vapor pressure. Vapor pressure in table 8.3 is saturation pressure. Okay, the question 2, you find surface tension coefficient of water at 5 and 60 Celsius. This one, the surface tension coefficient is another properties of water. So you can use the same table to find surface tension coefficient. Okay, this one is table 8.3. Okay, and surface tension coefficient is the last column in this table. You see it? The unit is Newton per meter. And at 5 Celsius, surface tension coefficient of water is 0.0749 Newton per meter. And at 60, we have here 0.0662 Newton per meter. Okay, so if you want to find the property of water, table 8.3. Okay, got it? Same table 8.3. Kinematic viscosity. Kinematic viscosity is viscosity divided by density of air and water at 20 Celsius. Okay. Kinematic viscosity of air. Firstly is of air. Okay, of air. So kinematic viscosity of air at we will have the equation here. Kinematic viscosity equal to viscosity divided by density. Okay, so air kinematic viscosity of air at 20 Celsius, you can use the table. Let me see which table. Okay, you have properties of air at 1 atmosphere pressure, at 1 atmospheric pressure. Table 8.9. Okay, So 0.9 at 20 Celsius. 20 Celsius, we have this one is a dynamic viscosity or viscosity. Okay, and after that we have kinematic viscosity, mu. Okay, so kinematic viscosity here is 1.516 times 10 minus 5. Okay, and you can double check. Kinematic viscosity will be equal to dynamic viscosity divided by the density. Here we have the density here. So this one will be equal to this one divided by 1.204. You can double check. Okay. So for air, we have the kinematic viscosity is at 20 Celsius is 1.516 times 10 minus 5. Okay, is 1.516 times 10 minus 5. This one is table 8.9. Okay, so for water at 20 Celsius, water properties of water, as I said, you can find from table 8.3. Okay, so now we go to table 8.3. 8.5, 8.4, 8.3. Okay, table 8.3. We have dynamic viscosity, not kinematic viscosity. Okay, so you can find kinematic viscosity equal to dynamic viscosity divided by the density. Or here we have dynamic viscosity of water at 20 Celsius is 1.002 times 10 minus 3. Okay, so equal to viscosity or dynamic viscosity divided by density. This one is at 20 Celsius. At 20 Celsius, and viscosity of water at 20 Celsius is 1.002 times 10 minus 3. Okay, you have from table 8.3 divided by density of water 1000. So you have this one is 1.002 times 10 minus 6. Okay, this one from table 8.3. You have the properties of water from table 8.3. Next one, the gas constant R for air at standard condition. The gas constant R for air. Okay, so we have table 8.1. Ideal gas specific heat and of some substance, gas constant, mole mass. Okay, table 8.1. For air, gas constant R is 0.87. But remember that the unit is kilojoule per kilogram Kelvin. Okay, and SI unit we have is joule per kilogram Kelvin. Okay, so I highly recommend that before any calculation, you convert gas constant R from kilojoule per kilogram Kelvin to joule per kilogram Kelvin. It means it's 287. Okay, so this one is 0.287 kilojoules per kilogram Kelvin, or equal to 287 joule per kilogram Kelvin. This one in SI unit. Okay. Next one, the lapse rate B in US standard atmosphere below 10,000 meter altitude. With B is change in temperature divided by corresponding change in the altitude. Lapse rate divided by corresponding change in altitude, and the unit is Celsius per kilometer or Kelvin per kilometer. Okay, this one. So for lapse rate, B equal to change in temperature divided by change in altitude. Okay, and for this question we can use table 8.11, this one. So table 8.11, 8.6, yeah, the properties of the atmosphere's high altitudes. So in this case, because the lapse rate B equal to change in temperature divided by change in altitude. So for example, if you want to find the lapse rate between 1000 and 2000 meter altitudes, it's going to be equal to temperature at 2000 minus temperature at 1000 divided by 1000 meter. Okay, so here is the temperature and the first column is altitude. For example, between 1000 meter and 2000 meter, you will have B equal to T at 2000 minus T at 1000. Because the unit is Celsius per kilometer, so you can convert from 1000 meter and 2000 meter to kilometer, equal to 2 minus 1 kilometer. And this temperature is at 2000 meter altitude we have 2 Celsius, and at 1000 is 8.5. It's going to be equal to 2 minus 8.5 divided by 1 or equal to minus 6.5 Celsius per kilometer. It means when you go up 1 kilometer, the temperature decrease 6.5 Celsius. Okay, and this one is correct to the lapse rate. B is correct for the altitude from 0 to 10,000 meter altitudes. Okay, you can double check from 0 to 10,000. Lapse rate is minus 6.5 Celsius per kilometer. But when the altitude is higher than 10,000, you see the temperature is almost constant here. So the lapse rate B in this case is not applied for the altitude higher than 10,000 meter altitudes. Okay. Next question: boiling temperature of water at 8,000 meter altitude. Boiling temperature at 8,000 meter. For this question, I think the subject coordinator have the solution for you on your test online already. Okay, so please have a look at the solution of this question on your test online. Okay. Next one, the sound speed in the air at the sea level and at 8,500 meter altitude. To find sound speed, as I said in the tutorial 1, we have two ways to find sound speed. We have sound speed from equation. Sound speed equal to square root of K R T, with K is a specific heat ratio, R is gas constant. You can find from table 8.1. This one you can find from table 8.1. Okay, and T is the temperature in Kelvin scale. Or you can find this one from the table 8.11. Okay, so you in the table 8.11 the speed of sound here at the sea level 0 meter altitude is 340, and at 8,500, yeah, 8,500, between 8,000 and 9,000, you can find based on interpolation equation. Okay, interpolation equation. You remember interpolation equation? For interpolation equation, for example, here in this case at 8,000 meter altitude, you have sound speed is 8,000. You have sound speed is 308.1. Okay, 308.1. At 9,000 meter altitude, you have sound speed a 303.8, 303.8, okay, and you have to find the sound speed at 8,500 meter altitudes, and this one sound speed I. So the interpolation equation shows you that 8,500 and minus 8,000 divided by 9,000 minus 8,000 equal to sound speed A minus 308.1 divided by 303.8 minus 308.1. Okay, this one is the sound speed. So from this one you can find sound speed at 8,500 meter altitude. Okay. So for sound speed in the air, you have two ways, one equation, one table. Okay. Next question. You have the maximum diameter of 5 cm long circular cylindrical steel needle with the density is 8,000. Next question. You have to find the maximum diameters of a 5 cm long circular cylindrical steel needle with the density is 8,000 kg per meter cube. This can stay afloat on water surface at 20 Celsius. Okay. So for this question, we have a needle. This needle afloat on water surface. Okay, and this one, the length L is 5 centimeter. With the density of the needle is 8,000 kilogram per meter cube. That's gonna stay afloat on water surface with temperature is 20 Celsius. You have to find the diameter D. Okay. So firstly, to the needle can float on water surface, it means the force is balanced. And how many force apply to this needle? Firstly, we have weight of the needle is downward, and upward we have another force is surface tension force Fs. So this needle floats on water surface when we have Fs equal to weight. Okay, Fs equals to weight. And how to find the weight of the needle? Weight of the needle will be equal to the density of the needle times the gravity times the volume. Okay. Density of the needle and the volume, this one, volume of the needle, because the needle is a circular cylinder. So the density of the needle will be equal to pi d square of 4 times L. Okay. So the weight of the needle will be equal to rho gravity pi d square of 4 times L. This one is the weight of the needle. And surface tension force Fs. Surface tension force will be equal to surface tension coefficient times the contact length. We have the contact length. It's between the needle and the water surface. And how to find the contact length? If we see from the top view, here, the eye here, the contact length between the needle and water surface will be is a rectangle. Okay, with this one is L, this one is D. So the contact length in this case rho will be equal to L plus D plus L plus D, or equal to 2L plus 2D. Okay, 2L plus 2D. So when we have surface tension force equal to the weight, so the surface tension coefficient 2L plus 2D will be equal to density of the needle times gravity times pi d square over 4 times L. Okay. With L, here is 5 centimeter. So when we convert it to SI unit meter, is 0.05 meter. Gravity 9.81, and the density of the needle is given in the question is 8,000 kilogram per meter cube. L here is 0.05 meter. Surface tension coefficient, this one you can find from the table. A properties of saturated water, the last column is surface tension coefficient. At temperature 20 Celsius, we have surface tension coefficient is 0.0727. Okay, 0.0727. So you see in this equation, from one equation you can find one variable, and the variable in this case is d, the diameter. Okay, so from here you can find d, and d here you have d is 0.00154 meter, or equal to 1.54 millimeter. This one is the maximum diameter. Okay. The last question. A pump is used to transport water to higher reservoirs. If the water is 20 Celsius, you have to determine the lowest pressure that can exist in the pump without cavitation. Why we have the cavitation? The cavitation occurs if at the pump inlet, at the pump inlet we have bubble. And why we have bubble? We have bubble when the water boils. Okay, it means the cavitation occurs when water boils at the pump inlet. And why water boils at 20 Celsius? Because the pressure at the pump inlet is smaller than vapor pressure at 20 Celsius. Okay, so it means the pressure at the inlet must be higher or at least equal to vapor pressure at 20 Celsius. And vapor pressure at 20 Celsius you can find from table 8.3. 20 Celsius, vapor pressure is 2.339 kPa. 2.339 kPa. Okay, so it means the lowest pressure at the pump inlet is 2.339 kPa. The cavitation is not occurs as a pump inlet. Okay, thank you.